Today, we're diving into a super clever algorithm called ROFSL. It's designed to do one very important thing: protect collaborative artificial intelligence from saboteurs. And it tackles one of the biggest security headaches in modern AI. So let's start with a big question. How can an AI possibly learn from all of our data without ever actually seeing it? Well, it sounds a little like magic, but it's the core promise of a technology called federated learning. It's a way to train a single, powerful AI model using data from tons of different places, think hospitals or even our phones, all while keeping everyone's data completely private. The easiest way to think about it is like a huge team of cooks, and they're all in their own separate kitchens. They're all working together to perfect one grand, complex recipe. But here's the thing: none of the cooks ever share their secret ingredients. They just work together to make the master recipe better. And in this whole setup, the central server, that's the head chef calling the shots. Okay, so here's the play-by-play. First, the head chef, that's our server, sends out a base recipe, which is the initial AI model. Then each cook or client gets to work, tweaking that recipe, using their own private ingredients, their local data. They don't send the ingredients back. Oh no, they just send back their notes on how to improve the recipe. These notes are the model updates. Finally, the head chef gathers up all those notes, combines the best ideas, and creates a new and improved master version of the recipe. And then the whole cycle just starts over. Now, this all sounds fantastic, right? But what happens if some of those cooks aren't just cooks? What if they're actually saboteurs and they're intentionally sending back terrible advice trying to ruin the whole dish for everyone? Well, in the world of AI, that's what we call a Byzantine attack. It's when these bad actors, these malicious clients, deliberately inject faulty, poisoned updates into the system. And their goal is pretty simple. They want to sabotage the entire learning process and make the final AI model totally useless, or maybe even worse, make it do something harmful. Of course, people have thought about this in their traditional defenses. One of the most common is something called robust aggregation. It tries to spot the bad recipe notes by looking for the outliers. The suggestions that are wildly different from everyone else's, and it just lowers their influence. But here's the catch, the big flaw. This whole defense relies on one very fragile assumption: that the good guys outnumber the bad guys. The moment the saboteurs form a majority, the whole system just completely falls apart. So that leads us to the million-dollar question. How do you possibly protect the AI model when you can't trust most of your participants? How does our head chef save the recipe when the kitchen is absolutely full of saboteurs? Well, this is where our hero, ROFSL, comes into the picture. The name stands for Robust Federated Learning via Server Learning. And what it does is give the head chef, that central server, a powerful new toolkit to defend the model. The core idea here is, honestly, it's pretty revolutionary. The researchers themselves put it perfectly. ROFSL lets us create a situation that acts like an honest majority, even when in reality, most of the participants are malicious. And how does it do that? By turning the server itself into an active, honest learner that can double-check the work of all the other clients. So ROFSL uses this really powerful three-part strategy. First, there's server learning, where the server itself gets in on the training action. Next, it uses what's called intelligent filtering to find and toss out the malicious updates. And finally, it takes the trusted results that are left and applies that robust aggregation we talked about. It's this 1-2-3 punch that makes it so incredibly effective. Okay, let's really get into this, because this is the genius part. How in the world does the server, which can't see anyone's private data, figure out which updates are coming from the saboteurs? The secret is that the server has its own little cookbook, a small private dataset that it keeps all to itself. And here's what's so cool about it. This dataset doesn't have to be perfect, or even the same type of data the clients have. As you can see here, the client's data on the left is different from the server's data on the right. The server's data can come from a totally different source. It can be synthetic, it doesn't matter. The point isn't for the server to solve the exact same problem, it's for it to have a trusted cheat sheet to give it a general idea of what a good, helpful update should even look like. Now, using this cheat sheet, the server has two main ways to filter out the bad advice. The first is an angle-based filter, which is kind of like a direction check. It just asks, hey, is this advice generally pointing in the right direction compared to where I think we should go? But the much more powerful method is the loss-based filter, or what I like to call the impact score. In machine learning, loss is just a number that tells you how wrong the model is, so lower is better. This filter actually scores each update on whether it really makes the model better on the server's own private data. And this loss-based filtering, this is the absolute key to ROFSL's success. For every single update it gets, the server basically runs a little test. It calculates an impact score that measures how much that update would improve the model. The updates from the saboteurs, the ones designed to cause harm, well, they're going to get a really low or even a negative score. So the server just sorts all the updates by their score and throws out the ones at the bottom. It's just like our head chef testing each new recipe idea on a small private batch, seeing if it makes the food better or worse, and only keeping the notes that actually work. So, the theory sounds great, but does this whole smart chef strategy actually work when the kitchen is full of saboteurs? Can it really handle a majority of bad guys? All right, let's take a look at the results. So this first chart shows what happens with the old methods. The server is not doing its own learning and filtering here. Along the bottom, you have beta, which is just the percentage of bad guys, from 0 to 70%. And on the side, you have the model's accuracy. Now look what happens. As long as the attackers are in the minority, under 30% or so, everything's fine. But watch as that number crosses 40%. The accuracy just completely collapses. It tanks, falling all the way to 10%, which is basically just random guessing. The system is totally broken. Okay, but what happens when we flip the switch? What happens when we turn on RFSL's server learning and that intelligent filtering? This is where the server gets to use its private cheat sheet to check everyone's homework. And this chart just says it all. The blue line, that's the standard method we just saw. It still falls off a cliff. But look at that orange line. That's ROFSL using the powerful loss-based filter. Even as the number of attackers goes past 50%, all the way to 60%, the orange line stays high. The model is still accurate, still effective. Sure, it degrades a little bit, but it doesn't collapse. It survives the storm. All because the server is actively finding and throwing out the poison before it can ruin the whole recipe. Let's just pause on that for a second, because the difference here is it's stark. When 60% of all participants are actively trying to sabotage the system, the standard defense gives you a model that's only 10% accurate. That's completely useless. But with ROFSL's server learning switched on, the model's accuracy is around 55%. That is the difference between total system failure and a model that is still useful, functional, and effective. So really, the big takeaway is that this combination, giving the server its own little dataset and empowering it with intelligent filtering, creates this incredibly powerful defense for collaborative AI. And why does this matter? Well, this is a huge step forward. It could let us do secure, privacy-preserving AI training in situations we used to think were just way too risky, in these zero-trust environments. Imagine banks working together to spot fraud, or hospitals sharing insights to fight disease, all without ever exposing their sensitive data. And now with a way to stay safe even when they can't be sure who to trust? The researchers end their paper by looking to the future, and they leave us with a really exciting question. Right now, ROFSL is amazing at ignoring the bad guys, but what if it could go one step further? What if the server could actually learn to keep track of which clients are consistently sending bad updates and not just filter them out, but actively identify and ban them from the team entirely? Now that could be the next frontier in building AI systems that we can truly, genuinely trust.